just add water molecules because they already give you a number. You just it's like times 2 times 3, and then you just add the chemical to it. Gotcha.
Oh, before I forget, I have created a Dropbox for chapter 3 assignment. It will be due. Hold on 1 minute. It will be due. That's. Okay, we'll be due on the 19th, which is Friday. All right, so make sure that you upload it into that Dropbox by then. All right, because we're finished with chapter 3, we're going to move on to chapter 4 now. And again, a lot of review will be involved in this particular chapter. So again, I'm going to try to go through it as quickly as possible. All right. So now we're going to look at reactions, chemical reactions in aqueous solution. All right. So first thing we're going to talk about is the electrical properties of aqueous solution. And basically, there are 2 types of charges, as you all should know, that can exist in an aqueous solution. You can have positive or negative charges. So just to demonstrate how charges actually behave, we have this diagram here to illustrate how they interact with each other. So if you have 2 particles, right, suspended as shown here, which are neutral, there will be no attraction forces or repulsive forces, right? However, if you have 2 particles that are in the same situation, where one is positively charged and the other one is negatively charged, then of course there will be an attraction between them, right? Unlike charges will attract each other. And then over here, where you have this situation or this situation where both particles have the same charge, then there will be repulsive forces between them. So that's basically how charges behave, right? It's kind of similar to bar magnets. I'm quite sure as kids, you have played with bar magnets, right? Each bar magnet, if you have a bar magnet, you have the north and the south pole. They behave very similar in terms of repulsive forces and attractive forces between, well, in the case of attractive forces between unlike poles like north to south. But if you try to put 2 north or 2 south poles close to each other, there will be a repulsive force that exists between them. All right. Okay, so let's apply some of what we're talking about when it comes to solutions which contain ions. Now, what you'll find is that if you have an ionic compound, right, and the compound is either dissolved in water or if it is molten. Molten is basically a term that is used for substances which require a high temperature for them to melt, right? And this is particularly true for ionic compounds. If you want to convert a solid ionic compound like sodium chloride to liquid, you need to heat it to a very high temperature, right? So what you'll find in both situations is that the compound will form ions, which will be free-flowing and moving freely within either the molten situation or in a solution, right? Now, if you set up an experiment where you have 2 metal plates, we call them electrodes, and they're connected to an electricity source by wires, right? And you leave it to run for a while, what you'll find is that the negative ions will be attracted to the positive electrode. The positive electrode is called the anode. All right. Okay, so the positive electrodes is called the anode, and the negative electrode is called the cathode. All right. So the negatively charged ions will be attracted to the anode, and that's why the negatively charged ions are called anions, because they're attracted to the anode, right? And then the positively charged ions will be attracted to the cathode, so therefore they are called cations. All right. So basically, what we're doing, or what is happening here in this setup, is that you have an electric an electric flow through the external circuit right here through the wires, but you also have an electric current flowing through the solution, all right? And if you have done any physics, you know that electric current is basically a flow of charge, right? So the charge could be positive or it could be negative, right? So in the case of the external circuit here, the flow of charge would be the electrons flowing through the external circuit, while here within the solution or within the molten ionic compound, the flow of charge would be the negative ions moving towards the anode, while the positive ions moving towards the cathode, all right? So you have an electric current going through the external circuit and also going through the solution or the molten form of the ionic compound. All right, so okay. All right, so let's see what we have here. Okay, so I mentioned this before, the anode and the cathode. So I don't think I need to say anything more about that. Okay, so let me clear this here. Okay, now when it comes to solutions and their ability to conduct electricity, there are three categories, right? The first of which is what we call non-electrolytic solutions, right? And basically what that means is that these solutions cannot conduct electricity because these solutions do not have any free-flowing ions present in it, right? So the example that is shown here is a molar solution of methanol, right? Methanol is a molecular compound. When you dissolve it in water, it will dissolve, but it will not break up to form ions. So therefore, there are no ions present in the methanol solution. And therefore, as a result, the methanol solution cannot conduct electricity. So if you have the methanol solution, stick two electrodes in it, connect it to an external circuit, and you notice in this picture here, a part of the circuit is a light bulb. And you'll notice that the light bulb is not turned on. And that's because there's no electric current going through the external circuit. And that's because there's no electric current flowing through the non-electrolytic solution of methanol, all right? So because there are no ions, there's no current flowing through, and therefore there's no electricity passing through the solution. Now, a second type of category of solution when it comes to electrical properties are solutions that are called strong electrolytes, right? And in these solutions, what you'll find is that there's a high concentration of ions present in the solution. And therefore, as a result, because we have the ions flowing freely through the solution, then when you stick two electrodes in it and connect it to an external circuit, then you'll have an electric current flowing. And that is manifested by the bulb here being a part of the circuit, lighting up very brightly. And that's because the concentration of the ions present in this solution is relatively high. So therefore, it will allow for an electric current to pass through it as a result, all right? So those are strong electrolytes. And you know, an example of a strong electrolytic solution would be something like sodium chloride. Sodium chloride, when added to water, will undergo complete dissociation to form sodium and chloride ions, and therefore that solution will conduct electricity very well. The third category of solutions in this regard are known as weak electrolytes, and they're so called because unlike something like sodium chloride, these electrolytes only undergo partial dissociation. So therefore, as a result, the molar concentration of the ions in these solutions are relatively low, and as a result as well, the ability to allow an electric current to flow through will be limited. And therefore, that is manifested, as you can see in this picture, where the bulb does light up, but not as brightly as in the case of the strong electrolyte solution. All right, so those are the three categories. So I mentioned the example of a strong electrolyte here, sodium chloride. This example here of a weak electrolyte is acetic acid. Acetic acid undergoes what we call partial dissociation. We're going to talk about that shortly. The result of that partial dissociation is that the concentration of ions are relatively low. Okay, so those are the three categories of solutions. So let's talk about ion concentrations in solution. So this symbolism here will become important not only in Chem 1, but also in Chem 2. In fact, it's probably more important in Chem 2. These square brackets or square parentheses, whenever you see that, it means concentration of whatever is within the square parentheses, right? So if I gave you something like this, if I gave you something like, right? If I gave you something like this means the concentration of HCl is equal to 0.50 m, all right? So that's a symbolism that is used pretty much throughout chemistry when it comes to representing the concentration of whatever is within the square parentheses. All right, so with that said, let's look at what happens when we have a solution of 0.010 m sodium chloride solution, right? As we said before, sodium chloride is a strong electrolyte, and therefore what will happen in the case of sodium chloride is that it will undergo a complete dissociation to form sodium ions and chloride ions, right? And based on the stoichiometry of that dissociation, we can clearly see that whenever 1 mole of this dissociates, it forms 1 mole of sodium ions and 1 mole of chloride ion, right? So therefore, we can predict that if the solution was originally 0.010 m sodium chloride, that means that the concentration of sodium ions would be 0.010 m, and the concentration of chloride ions would be 0.010 m. So therefore, we can say also that the total, write this down, the total ion concentration, the total ion concentration in this case, total ion concentration in this case would be 0.020 m, right? Because you have to add this to this, right? So that's how we can tell the concentration of the ions based on the stoichiometry of the dissociation of the compound when added to water. I think I have another example here. Okay, let me just do another example. Let's say you're given a 0.010 m solution of potassium sulfate, all right? So again, you have to look at the dissociation of potassium sulfate. When that dissociates, you're going to get 2 potassium ions and 1 sulfate ion for every potassium sulfate unit that dissociates, right? So basically, we can say that the concentration of the potassium ion would be equal to 2 times the concentration of the potassium sulfate initially, so that would be 0.020 m, and the concentration of the sulfate, because of the 1-to-1 ratio between those two, would be 0.010 m. So therefore, we can say that the total ion concentration would be equal to 0.020 m plus 0.010 m, which would be equal to 0.030 m. And that's how you get a total ion concentration, all right? So the point here is that in order for you to determine the concentration of each ion present in a solution, you have to take into account the stoichiometry of the dissociation, right? You have to look at how many ions are formed, or I should say, how many ions of each kind are formed from the dissociation of one formula unit of the original ionic compound, all right? Okay, so moving on. Let me clear this first. Okay, so let's talk about acids. I think we defined acids earlier. Yes, we did. Acids are basically substances which, when added to water, produces H+ ions, right? Now, as far as acids are concerned, we can put them into 2 major categories, especially with respect to the electrical properties, right? You can have weak acids and strong acids, right? And basically those terms is pretty much the same as in the case of what we discussed before with respect to strong electrolytes and weak electrolytes, right? So strong acids are the ones that will undergo complete dissociation, right, to form ions, while weak acids undergo partial dissociation, all right? So that's the difference between strong acids and weak acids, right? Now, when it comes to representing the dissociation of weak acids, what we use is a double arrow. We use 2 arrows to write down or to indicate in the equation for the dissociation that the acid is weak. So I think I have an example here in the case of acetic acid, which we actually met earlier, right? So this is the acetic acid molecule, and these are the ions that are produced when it dissociates. And you'll notice we have 2 arrows here, right? What this indicates, right, is that basically the reaction goes in both directions, right? So the original acetic acid molecule will undergo dissociation to form what is called the acetate ion and the hydrogen ion, but also you're going to have the acetate and the hydrogen ion coming back together to form the acetic acid. So you have this back and forth taking place, right? Until you get to a state of what we call dynamic equilibrium. And again, for those of you who have to do Chem 2, then you're going to encounter equilibrium. It's a huge topic in general chemistry 2, which takes up about 3 chapters, right? And the basic underlying principle is that in equilibrium, you have reversible reactions which go back and forth, where the rate of the forward reaction will be equal to the rate of the reverse reaction. And that's exactly what is happening in this case. And as a result of that back and forth, the result is that the concentration of the acetate and the H+ ions will be relatively low, especially when compared to strong acids, where you don't have that back and forth, right? So that's basically true for all weak acids. And this is just basically showing you in the case of acetic acid. Down here, we have a ball and stick model representation of the same reaction, all right? The same dissociation. Okay, so that's basically how weak acids behave. And as stated here, organic acids, most organic acids are weak acids, and there's some inorganic acids also that are weak as well. Okay. Now, in the case of strong acids, they undergo complete dissociation, right? So you might be wondering, how can we tell the difference between a strong acid and a weak acid? Well, traditionally or conventionally, the formulas of strong acids are typically written with the hydrogens indicated first, right? As you can see here, in the case of hydrochloric and in the case of sulfuric. And then in the case of weak acid, the hydrogen that is released when it's added to water is written at the end of the formula. But I must say that this is not true in all cases when you read the chemical literature. Even though it's true in some cases in terms of how the formula of strong acids and weak acids are represented. So at this level, this is what I would say to you in terms of recognizing strong acids. These 6 acids must be memorized as strong acids. So make sure you commit these strong acids to memory. Hydrochloric acid, hydrobromic acid, hydroiodic acid, and then you have the oxide acids, nitric acid, sulfuric acid, and perchloric acids, right? So you need to remember these 6 acids as strong acids, right? Pretty much all other acids that you're going to meet at this level will be weak acids. And let me also say something about sulfuric acid, because sulfuric acid is a bit special in this regard. And as you can see, unlike other acids, sulfuric acid has 2 hydrogen atoms or ions that can be released, right? Now, the first ion can be released like this. All right. So you can have the release of 1 hydrogen ion from the molecule of H2SO4. Now this here, the HSO4 minus itself can release another hydrogen ion, right? But the thing about the second release is that the release will be weak. So this would be what will happen in the case of the hydrogen sulfate ion undergoing dissociation, right? So this dissociation is strong, right? In other words, all the molecules of sulfuric acid will be converted to H+ and HSO4 minus, but the HSO4 minus that is produced in this step will undergo a weak dissociation to form H+ and SO4 minus, all right? So sulfuric acid is a bit different from the other strong acids in that regard, all right? So you need to remember this. Sulfuric acid, the first dissociation is strong, but the second dissociation is a weak dissociation, all right? Okay, so you need to remember those 6 strong acids. All right, let me clear this and scroll down. All right, so when it comes to bases, the terminology strong and weak means the same thing as in the case of acids, right? So strong bases will undergo complete dissociation in water and will be good conductors of electricity. And these are typically ionic hydroxides like sodium hydroxide, sodium, magnesium hydroxide, and so on. All right. Weak bases, they are not as good conductors of electricity, and these are typically molecular compounds which interact with water to form hydroxide ions. And I think I may have an example here. And again, we use a double arrow representation to show that in the case of weak bases, it's a back and forth, right, until the system achieves equilibrium. So the example of a weak base here is ammonia, and they don't have the equation here, so let me show you. In the case of ammonia, what happens is that when you add it to water, this is what happens. You're going to have NH4 plus, ammonium ion plus hydroxide ions, right? And it's the formation of the hydroxide ions which makes solution basic, all right? And as you can see, you have arrows going back and forth, which means that the ammonium plus the hydroxide will reform the ammonia and water. So you have the back and forth taking place. And as a result of that back and forth between the reactants and products, the concentration of the hydroxide ions will be relatively low, and therefore the ammonia will be a weak base as a result of that. And also as a result, its ability to conduct electricity is relatively low as well. So that's basically what happens in the case of a weak base. Ammonia is not the only weak base, of course. In fact, most of the weak bases are organic in nature as well. All right. Okay, so that's as far as strong and weak bases are concerned. Okay, so in terms of the strong bases, you need to memorize these. All right. These are easy to remember because these are hydroxides from groups 1A and 2A, right? So, once you have the periodic table with you, then you can basically determine the strong bases based on what we just said here. And therefore, pretty much all of the bases that you will meet will be weak bases, all right? So make sure that you memorize these particular strong bases. Okay, this will be important, especially when it comes to something that we're going to meet later on, basically dealing with net ionic equations, all right? Okay, so let's talk about, excuse me, the neutralization reaction, which is the reaction between an acid and a base. Now, the products of the neutralization reaction would be water and another compound, which is called the salt, right? And the formula and makeup of the salt is dependent on the acid and base that is undergoing the reaction, right? Now, the term neutralization, before I get into the reaction itself, is a bit of a misnomer. And the reason I'm saying that is that the neutralization term is assuming that, okay, you have the acid, which is acidic, reacting with the base, which is basic, and therefore when they react, they form something which would be neither acidic or basic, but will be neutral. That's the premise, right? But it turns out that that will not always be true. In some cases, the salt will be acidic. In other cases, the salt will be basic. And yet in other cases, the salt will be neutral. At this stage, we won't get into that distinction, right? That's for Chem 2 again, right? So for now, we're just going to concentrate on what happens in a neutralization reaction. Now, what happens in a neutralization reaction, and here's an example, the reaction between hydrochloric acid and potassium hydroxide, is that the hydrogen from the acid will combine with the hydroxide from the base to form your water. And basically what remains, which would be the potassium, combining with the chloride from the acid, will combine to form your salt, which in this case would be potassium chloride, right? So that's basically how you determine the salt that is produced. The salt that is produced is formed from the positive part of the base coming together with the negative part of the acid, all right? So that's basically what happens in the case of a neutralization reaction. And see here. Okay, before we move on to that, so let me just do another example just to show you how you can determine the how you can write down the equation for a neutralization reaction. So let's say you're given sulfuric acid, and let's say it is reacting with aluminum hydroxide. Let's do that, right? So as we said before, the hydrogen will come together with the hydroxide to form water, right? And the other product, will be the result of the combination of aluminum with the sulfate. Now, in this case here, aluminum will have a +3 charge and the sulfate will have a -2 charge. So therefore, the formula for aluminum sulfate would be Al2 parentheses SO4 and then 3 here. So that would be the formula for the salt. And therefore, the only other thing we need to be concerned about is writing down the balanced equation. So we need to balance this. So basically, to balance this, we're gonna need a 3 here and a 2 here. And here we're gonna need 6 here, and that's it. And that would be the balanced equation for the neutralization reaction between the sulfuric acid and the aluminum hydroxide. So that's basically how you can write down or determine the neutralization reaction between an acid and the base. Okay, let me clear this here and continue. So let's talk about net ionic equations, right? So very often reactions in an aqueous solution involves combinations of ions. And what will happen is that you end up with a product which basically shows you which ions are directly involved in the reaction. And then there are some other ions which are not directly involved in the reaction, right? So the ions that are not directly involved, which remains unchanged in the reaction, we call them spectator ions, right? They are so called because they do not participate in the reaction. They basically just sit around and watch what's happening, right? So basically, once you identify the spectator ions, then all the other ions that are involved in the reaction directly are the direct participants of the reaction, right? So going back to the neutralization reaction that we just discussed here, right? The reaction between hydrochloric acid and potassium hydroxide to form water and potassium chloride, right? What you're going to find is that in order for you to determine what the net ionic equation is, you need to determine what the states of the different substances involved in the reaction will be, whether or not they're aqueous, liquid, gaseous, or solid, right? So in the case of this reaction, hydrochloric acid will be in an aqueous solution, potassium hydroxide will also be in an aqueous solution, H2O is always liquid, and potassium chloride is in an aqueous solution, right? Now, we call this in chemistry, in this process, we call this the molecular equation, right? And this is a bit of a misnomer again, because not all the substances involved are molecules, right? In fact, the only molecule here is water. All the other compounds, and HCl, I'm sorry, HCl is also another molecule. The potassium hydroxide and the potassium chloride are ionic, right? But that's a terminology that is used in this purpose, right? Now, in order for us to get to the net ionic equation, we have to ask ourselves, okay, what will be the actual state of the different substances in an aqueous solution? In other words, will any of these compounds undergo complete dissociation in an aqueous solution, right? And this is where memorizing those acids and bases that are strong will become important, as you're going to see here, right? So what we're going to determine is what is called the ionic equation based on the molecular equation that we have here. And I think I have that here. Okay, so this would be the ionic equation. So let me explain how we arrive at the ionic equation from the molecular equation. Okay, let's start with the HCl. In the case of the HCl, if you remember, HCl or hydrochloric acid is one of those strong acids that you need to memorize, right? And because it's a strong acid, we know that it undergoes complete dissociation, right? Which means that the HCl will dissociate to form H plus and Cl minus completely, right? So that's as far as the HCl is concerned. Now the potassium hydroxide, again, from what we said before, you need to memorize that it's a strong base, right? So therefore, it will undergo complete dissociation as well. So the potassium hydroxide will undergo complete dissociation to form K plus and OH minus. So that takes care of everything on the left side or the reactant side of the reaction. So now we go to the product side. And what do we notice? The first thing we notice here is that we have water. Now, water is a molecular compound. and therefore, because water is molecular, it will not undergo dissociation. So therefore, we simply just rewrite it as H2O on the right side, right? It will not break up to form ions. And then we get to the final product right here, KCl. Now, if you have any ionic compound in an aqueous solution, it will undergo complete dissociation, right? So therefore, it will dissociate to form K plus and Cl minus, right? So this is called the ionic equation, because this shows you all the ions that would be formed as a result of the dissociation of different substances in the molecular equation. So now that we have identified the ionic equation, the next step is that we have to identify the spectator ions. Remember I said that the spectator ions are those ions that do not actively get involved in the reaction. They remain unchanged as you go from left to right, right? So what you need to do in order to identify the spectator ions is identify those ions that remain unchanged. And if you look at this carefully, you'll see that comparing the left side to the right side, you'll see that the chloride ions are not involved in the reaction. They remain unchanged, right? So the chloride ions you can cancel out, as you can see here. And then the other ion that remain unchanged will be the potassium ions. So you can cancel those as well, right? So we cancel out those spectator ions, and then we write down what is left, and that would be the net ionic equation, which would be H plus reacting with K plus, reacting with OH minus on the left side, and then the right side, the only thing that remains would be the OH, or water, right? And therefore that would be the net ionic equation, right? So these are the steps that you'd follow to determine what the net ionic equation is. Basically, you start from the top, you identify those items that will undergo complete dissociation. That would be strong acids, strong bases, and any ionic compound in an aqueous solution. Once you determine what ions will be present in the net, or I should say in the ionic equation, you identify those ions that are common to both sides. Those are the spectator ions. Those are the ions that you will cancel out. Once you cancel out those ions, whatever remains will constitute the net ionic equation. All right. So we're going to see that, well, we have seen that in this case where we're dealing with a neutralization reaction, but you're going to see that also in other cases in this chapter. All right. Okay. Any questions about this? Any questions? Any questions? Any questions? All right. Moving, well, let me clear this first, and then we'll move on. Okay, moving along. Let me just briefly mention this. For those of you enrolled in my lab course, you're going to get some experience with what we call titration. Titration is basically a form of analysis where we use a solution. Well, there are different ways of different things done with titration. The one that you'll be doing, for those of you enrolled in my lab, is where you use a solution of a known concentration to determine the concentration of another solution based on the stoichiometry of the reaction between the solutes in a different solution, right? So this is just a brief description, of course. It's a bit more involved. Basically, what you're going to do is take one reactant and place it in a burette, right? A burette is a long cylindrical piece of glassware. They come in different sizes. The ones that we have in our lab here is a 50 ml burette. I think the smallest one I've seen is a 20 ml burette, right? So basically you're going to have, I think I have a picture of it, actually. No, I don't. Okay, so let me see if I can find the picture online so that you have an idea as to what we're talking about. Burettes, B-U-R-E-T. Let me say burette chemistry. Images. Okay, trying to find this. Okay. This picture here shows you basically what you'll be doing in the, again, for those of you enrolled in my lab course, I can get a bigger picture of this here. Okay, so basically, this picture shows you, Okay, let me see if I can get this larger version of this here. Okay, so this picture basically shows you what you'll be doing in the experiment, right? So I was looking for a picture of the earth. I wanted to get the whole thing, but I can use this here to show you. This is a long cylindrical piece of glassware. The important thing about Burex that you need to know is that it doesn't measure the amount of liquid that is in it. It measures the amount of liquid that is dispensed from it, right? And the way it's graduated, you're going to see in the lab, it's graduated such that you start with 0 at the top, and then depending on the size, since we're dealing with a 50 ml Burex, you're going to have 50 ml down here at the bottom, right? So typically what we would do is that we would add our liquid to the Burex, and we have to, of course, ensure that the stop top is closed, right? When you're pouring your liquid in it. And then you can get it to the 0 mark or close to the 0 mark. And then what you can do is open up the Burex, the stopcock here, to allow the solution to run through. And then when you turn it off, you take the new reading. And the difference between the initial and final volume reading would represent the amount of liquid that you just dispensed from the Burex, right? So in the experiment that you guys will be doing, in the titration experiment, if I remember correctly, you'll be determining the percent of acetic acid in vinegar, I think it is. So what you're going to do is you're going to fill your Burex with your base, sodium hydroxide or potassium hydroxide. In your early math class down here, you're going to have your acidic solution. So I think in the experiment that you'll be doing, you'll be working with acetic acid. So you're going to have your acetic acid solution, which is diluted to a certain extent. And then you're going to add your indicator, right? The indicator is basically a dye which takes on a color depending on the acidity or basicity of the solution, right? The indicator that you'll be working with is a compound, a dye called phenolphthalein. Phenolphthalein is colorless in acid and pink in base, right? So when you add your indicator to your acid solution, it's going to be colorless, right? You're going to place it under your Burex. You're going to take your initial reading, right? And then you're going to open the stopcock and run the sodium hydroxide into your acidic solution. And eventually what will happen? Initially, the solution will be colorless, and then eventually the solution is going to become pink. When that happens, you're going to turn off the stopcock, and then you're going to record the second volume, right? And then based on the concentration of the base and based on the volume that you have dispensed into the acid solution, you can do some calculations, and basically you can determine, again, I think the experiment that you'll be doing is the analysis of acetic acid. So you can determine the percentage of acetic acid in vinegar. And that's basically what's involved in titration. So as I said before, for those of you enrolled in the lab, you're going to get the opportunity of carrying out that experiment, which is a bit of a fun experiment, all right? So that's basically what happens in titration. And there are different types of titrations. The one that we just discussed is what we call an acid-base titration, but you can have other forms of titration. You can have precipitation titration, you can have redox titration, and others, all right? Okay, so let me continue on. Okay, so let's talk about certain gas formation reactions, which is a form of acid-base titration. There are certain reactions where acids are involved when added to substances containing particular ions will produce gases, right? So the first one that you notice here is the reaction between H plus. So these are all net ionic equations, by the way, all right? So this first reaction is the reaction between H plus and the bicarbonate ion. And as you can see here, produces carbon dioxide and water. And a similar reaction will take place if instead of bicarbonate, you use the carbonate ions. If you add acid to the carbonate ion, again, you're going to get carbon dioxide and water, right? And that will be manifested by bubbles. The carbon dioxide being produced will be shown as bubbles emerging from the solution. And this reaction you can actually do at home. This is safe enough to do at home. As you can see here, this person is squeezing lemon juice onto baking soda. Baking soda contains the bicarbonate ion. So you can do this at home. You're going to see bubbles form. The bubbles form is due to carbon dioxide. Instead of lemon juice, you can use vinegar, right? Vinegar contains acetic acid. So if you add a few drops of vinegar, again, to baking soda, same thing is going to happen, right? You're going to see bubbles, right? So that's what happened in the case of adding acid to either the bicarbonate or carbonate ions or any compounds containing these ions. Now, in the second pair, where we have the acid being added to a compound that contains either the hydrogen sulfide or the sulfide ions, you're going to get sulfur dioxide being produced as well as water, right? Now, this reaction, I would definitely not recommend you do at home, right? Because sulfur dioxide, if you're exposed to it, you start coughing and choking and all of that, right? So this is something that you would not do at home to see. But basically, this is another gas forming reaction, very similar to what we discussed earlier with respect to bicarbonate and the carbonate ion. Now, the last pair of reactions is a reaction where acid is added to hydrogen sulfide, anything that contains the hydrogen sulfide ion or the sulfide ions, right? In these two cases, you're going to end up with a gas being formed, and that gas is known as hydrogen sulfide, right? And in this particular case, you definitely don't want to do this one at home for two reasons. One, hydrogen sulfide is an awful smelling gas, right? It has the smell of rotten eggs, right? If you're familiar with that smell, the spoilage of rotten eggs is actually as a result of the formation of hydrogen sulfide as a result of the decomposition of the proteins in rotten eggs, all right? So that's one reason. The other reason is that it's very toxic, right? If you find yourself in a room filled with hydrogen sulfide, apart from the offensive odor, eventually what would happen if you decide to stay in the room is that you won't smell it anymore. And by then it will be too late because hydrogen sulfide will build up to a very toxic level in your blood, and therefore more than likely you will not survive because it's very poisonous. So don't do this at home. Don't do this reaction at home at all. All right. Okay, so those are just basically some gas forming reactions associated with the reaction of acids with particular anions. All right. Now we're going to get into what are known as precipitation reactions. And as the name suggests, what is happening in these reactions is a formation of what is called a precipitate. So what's a precipitate? A precipitate is a solid that is formed as a result of mixing two clear solutions, right? So you have two clear solutions into, let's say, test tubes, and you pour one into another, and you have the spontaneous formation of a solid. And that is demonstrated in this picture right here. And if I'm not mistaken, this is actually the reaction between lead, 2 nitrate, write on the equation here, lead 2 nitrate, aqueous, and potassium iodide, aqueous. And the products of this reaction would be lead 2 iodide solid and potassium nitrate aqueous. And to balance this, we need a 2 here and a 2 here, right? So you'll notice in this particular reaction, one of the two products will be a solid resulting from mixing 2 aqueous solutions. One of them is lead 2 nitrate and the other one is potassium iodide, right? So that's an example of what we call a precipitation reaction, where you mix 2 solutions together and you end up with a product which is a solid. Now, how can we predict such a reaction will take place? Because not all 2 aqueous solutions of ionic compounds will result in the formation of a solid. Well, there's a table that is present in your in Canvas, the same table. I don't think it's the last page, but it looks something like this. All right. Well, it's not really a table, but it's just basically a chart, which you can find useful in predicting whether or not a particular reaction will result in the formation of a precipitate. Now, the key thing you need to remember is that if a compound is a precipitate, or if a precipitate is formed, that precipitate is formed as a result of the compound not being soluble in water, right? So if the solubility of the compound is very low, then basically it will not dissolve, will form a solid as a precipitate, right? So what we have here are what we call solubility rules for different compounds, right? So basically, based on these rules, you can make predictions as to whether a particular product of a reaction will either remain in solution or form a solid as a precipitate, right? So let me just point out a few features of this table. The first line says almost all nitrates, acetates, perchlorates, group 1A metal salts, and ammonium salts are soluble. So basically what this is saying is that any compound that fits into this description will dissolve in water and therefore will not form a precipitate. Look at this line right here. It says most chlorides, bromides, and iodides are soluble, but there are exceptions. Lead 2 plus, silver plus, and mercury 1. This is called mercury 1, by the way, right? So basically, any compound that contains chlorides, bromides, and iodides will be soluble, with the exception of compounds of these ions, which are lead, silver, and mercury 1, right? And so on and so forth for the rest of the chart. So you can use this chart to make predictions as to whether or not a particular ionic compound will dissolve in water, or if you have a precipitate that will be formed, right? And this is just giving you some examples of some precipitation reactions and their practical applications. So for example, this one, the first one, is using water purification. Let's say you have a lot of aluminum present in water, you can add hydroxide ions that will form a gelatinous precipitate, which you can remove from your water. This here is used to remove phosphates from wastewater in sewage treatment, and so on and so forth. So there's some, real applications of precipitation reactions. Okay, so I think the best way to learn how to write down the net ionic equations of precipitation reaction is to do an example. So what I'm going to do is get out of this, and let me go to Word. Bring this up. And draw. Okay, so here's a typical problem involving a precipitation reaction. In fact, I'm going to use the same example that I showed you earlier. So the example that I showed you earlier is the reaction between lead 2 nitrate, aqueous, and potassium iodide, aqueous. And let's say we did not know if the products would be soluble in water, right? So basically, we can predict the products when you have 2 ionic solutions mixed together, right? Those of you who did introductory chemistry, which should be all of you, especially if you're in my class, we talked about double displacement reactions. We have an exchange of ions, right? So we can predict that one of the products of this reaction would be lead 2 iodide, and the other product would be potassium nitrate, right? Now, the thing is, we have to make a prediction as to whether or not these compounds would be soluble in water. So that means we have to go back to the table that I showed you earlier. So let me go back to the table. This table here, right? So based on this table, first question we have to ask ourselves is potassium iodide soluble in water? So we go to the table, right? And based on the information provided here, no, not potassium, what am I saying? Lead 2 iodide, that's what I meant to say. So is lead 2 iodide soluble in water? So according to the table, most iodides are soluble, but one exception is lead 2 plus, right? So basically, lead 2 plus would not be soluble in water, so therefore, we put S here to indicate that a solid is formed, right? And then now we do the same thing. We ask ourselves, is potassium nitrate soluble in water? Go back to the table. And what do we see here? Almost all nitrates, acetates, perchlorates, and group 1A metals. So potassium is in group 1A, and nitrates, almost all nitrates are soluble. So therefore, we can say that potassium nitrate is soluble, and therefore we can put AQ because it will be soluble in water, right? Now, this would be, again, the molecular equation. Again, bit of a misnomer because in this case, there are no molecules formed, but that's a terminology that is used in chemistry for this reaction or this equation, right? Now, if you remember when we were doing the neutralization reaction to determine the net ionic equation, the next step was to find or determine the ionic equation. And if you remember what we said, in order for us to determine the ionic equation, we have to determine which ionic compounds will dissolve in water, right? Now, in this case, it's a bit easier because we have aqueous here, solid here, aqueous here, right? So in the case of lead 2 nitrate, because it's an ionic compound in an aqueous solution, we know that that will completely dissociate. So therefore, the ions formed as a result of the dissociation of lead 2 nitrate would be Pb2 plus aqueous and the NO3 minus aqueous, right? But because we have a 2 here, we need to multiply that by 2, right? That's very important, okay? So that takes care of the lead 2 nitrate. Then, oh, before we do that, I forgot one important thing. And that is we needed to balance this equation to begin with, right? How could I forget? Okay, so to balance this, we need a 2 here, we need a 2 here, right? So that's very important, right? Okay, so continuing to look at what will dissociate. In the case of potassium iodide, aqueous, that will dissociate to form potassium ions and iodide ions. So because we have a 2 here, that multiplies everything. So therefore, we have 2K plus aqueous plus 2N minus aqueous. All right? Okay, so that takes care of everything on the reactant side. So on the product side, we have now lead 2 iodide, right? It's not aqueous, it's in a solid state. So therefore, we don't need to do, we should not dissociate it. So basically, it will exist as PbI2 solid, right? Because it's in a solid state, it's not in an aqueous state. And then lastly, we now have potassium nitrate. We have 2 of them. So we need that to dissociate to form 2K plus aqueous and 2 NO3 minus aqueous. And that's it for the aqueous. Sorry, AQ. All right? And that's it for the ionic equation. All right? So now we get to the net ionic equation. And if you remember what we did in the case of the neutralization reaction example that we worked, in order to get from the ionic to the net ionic equation, we identify the spectator ions. Spectator ions are those ions that remain unchanged as you go from reactants to the products. So my question to you is this: what are the spectator ions that you can identify from the ionic equation? What are the spectator ions? Remember, the spectator ions are those ions that remain unchanged as you go from left to right of the ionic equation. Yes, ma'am. Exactly, the 2 NO3 minus ions. Anything else?
2 potassium.
The 2
Potassium.
potassium ions, exactly. Right? So therefore, what is left would be Pb2 plus aqueous plus 2I minus aqueous to give PbI2 solid plus, oh, not plus, that's it. All right, and that would be, folks, the net ionic equation. So this is the actual reaction taking place. The lead 2 plus combining with the iodine to form the lead 2 iodide solid, right? So that's basically how you determine the net ionic equation for a precipitation reaction, right? Okay, any question about it? Any question? Okay, let's go back to the point. Okay, so oxidation and reduction. Now I'm going to take some time with this because I don't think you'd have met this in any great detail in your previous chemistry experience. So I'm going to go a bit slower when talking about this. All right, so what do we mean by these terms? Well, firstly, there are some reactions that involves the transfer of electrons from one species to another, right? So basically, one substance will be losing electrons, and those electrons will be transferred to the other substance, right? So the substance that is undergoing the loss of electrons, we say that that substance is undergoing oxidation, and therefore it is being oxidized, right? And then the other substance that is receiving the electrons, we say that that substance is being reduced, right? And we call the shorthand terminology that we use for these types of reactions. We say that these are redox reactions. Redox is basically abbreviation for reduction oxidation, right? And that is because in these reactions, if one substance is being oxidized, then another substance has to be reduced. You cannot have one without the other, right? So I think I have a simple example, but before we get to the example, let me talk about this concept of the oxidation number, which is important. Basically, the oxidation number is a way of indicating the level to which a particular atom of an element is oxidized, right? And the definition here is that it is the charge the atom would have in a molecule or in an ionic compound if the electrons are completely transferred from one atom to another, right? So there are some rules that you need to know to determine the oxidation number of an atom in different situations, right? The first rule is probably the easiest rule. Talks about the fact that if you have an atom or an element in a free state, so it's not combined with anything else, right? Then you can automatically assume that the oxidation number of that element is zero, right? So if you have oxygen, in fact, I have some examples here. If you have oxygen or phosphorus or lead, any element by itself, the oxidation number of those elements will be zero, right? So that's the first rule that you need to know. And that's the easiest one. The second one is also easy. If you have a monatomic ion, right? Whatever charge it has, that charge will be equal to the oxidation number of that particular element in that ion. So here are some examples. If you have a lithium ion, which carries a +1 charge, then its oxidation number is +1. If you have an iron 3 ion, which carries a +3 charge, then its oxidation number is +3. And if you have an oxide ion, which has a -2 charge, then its oxidation number is -2. So if you have a monatomic ion and it carries a charge, whatever that charge is, it's the same thing as the oxidation number of that ion. Okay, rule number 3. And this is specific when it comes to oxygen, right? In all the compounds that oxygen is present in, then the oxidation number of oxygen is usually -2, right? The exception is hydrogen peroxide and any compound that contains the peroxide ion, right? So if oxygen is in a compound, right, usually the oxidation number of oxygen is -2, but if you have oxygen in hydrogen peroxide or oxygen in any compound that has the peroxide ion, then its oxidation number is -1. And let's see here. I need to add a little statement here. Well, not a statement, but like an additional piece. This is for oxygen in its compounds, right? In other words, oxygen is present in a compound, not oxygen by itself. Oxygen by itself would have an oxidation number of 0, as we said before, because it's an element. But if oxygen is combined with something else, then the oxidation number is usually -2. But in the case of peroxides or hydrogen peroxide, the oxidation number of oxygen is -1, right? Okay, so that's rule number 3. Continuing, rule number 4, and this is a rule that deals with hydrogen. And I need to add the same thing here. I'm just noticing that. In the case of hydrogen, its oxidation number is usually +1 in its compounds. All right, so in this case, hydrogen is bonded to something other than hydrogen. All right, so what we're saying here is that if you have hydrogen combined with something else, right, then usually the oxidation number is +1, right? However, if it's bonded to a metal, then the oxidation number of hydrogen is -1, right? So it's +1 if hydrogen is bonded to a nonmetal, but it's -1 if hydrogen is bonded to a metal. I think I may have an example. If not, I'll just show you. Okay, I don't have an example here. So let me give a couple of examples. So if you have, let's say, H2O, right? the oxidation number of hydrogen is equal to +1 because because hydrogen is bonded to a nonmetal, right? But if you have something like magnesium hydride, right? In this case, the oxidation number of hydrogen is -1 because in this case, the hydrogen is combined with a metal, right? So that's what rule number 4 is saying. If hydrogen is bonded to a nonmetal, the oxidation number is +1. But if hydrogen is bonded to a metal, then the oxidation number is -1, all right? Okay, rule number 5 deals with different groups. If the metal, and again, these are all in their compounds. So let me add that here just to be complete. All right? For group 1A metals, if they're combined with something else, then the oxidation number is +1 always, right? For group 2A metals, the oxidation number will be +2 if they're combined with other elements. And fluorine is very unique because fluorine, if it's bonded to anything, its oxidation number is always -1. All right? So that's another rules that are specific to different elements. All right? Okay. Let's see what's next. And then the last rule, which basically helps you to determine the oxidation numbers of other elements. The sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge of the molecule or ion. And I think I have an example of this. Let me clear this here. And let's see here. Okay, so here's the example. Let's say you're given the bicarbonate ion, and you're asked to determine the oxidation numbers of all the atoms present in this ion, all right? Now, based on earlier rules, we know what the oxidation number of hydrogen is and what the oxidation number of oxygen is. Remember, hydrogen is +1 and oxygen is -2, right? But we didn't see any rule dealing with carbon. So how do we determine the oxidation number of carbon? Well, the answer lies in this rule right here, because what this rule says is that the sum of all the oxidation numbers of all the atoms in an ion will be equal to the charge on the ion. So basically, we're going to set up a simple equation, right? Where we know that oxygen has an oxidation number of -2, hydrogen has an oxidation number of +1, but we do not know what the oxidation number of carbon is. So the question sign represents the oxidation number of carbon, right? So what we do is add up the oxidation numbers of everything according to the formula. So hydrogen is +1, right? Oxygen is -2, but because we have 3 of them, we multiply by 3, right? And then we put the question sign, which represents the oxidation number of carbon. So 3 times -2, which is 6, plus 1. So 6 minus 6 plus 1 gives you -5. And that will be equal to the sum of the charges present in the ion, which is -1, right? And therefore, when you solve for carbon, you see that carbon works out to have an oxidation number of +4. So that's how you can determine the oxidation number of other elements that were not described in the previous rules, based on rule number 6, right? The sum of the oxidation numbers of all the elements in the compound or in the molecule or polyatomic ion will be equal to the charge carried by the molecule or the polyatomic ion, all right? Okay, any question about this? Any question? Any questions? Okay, so how do we identify redox reaction? Well, basically, as I said before, in a redox reaction, we have the transfer of electrons from something being oxidized to something being reduced, right? What is corresponding to that is a change in the oxidation number of some species involved in both reactants in the reaction. So how do we track that? We look at the oxidation numbers of the different atoms present in the reactants and how they change as you go from reactants to products, right? So basically, if the oxidation number increases for one particular atom, then basically oxidation is taking place for that atom. And if the oxidation number reduces, then reduction would have taken place for that atom. So the oxidation, where there is an increase in the oxidation number, that corresponds to electron loss. If the oxidation number decreases, then that corresponds to a gain of electrons. So we're going to use a simple example of a redox reaction so that you can see how the oxidation number changes. So what you're looking at here is a simple experiment where we take magnesium in the form of magnesium ribbon and we submerge it in a solution containing copper 2 sulfate, right? And you let it sit for a while, and then what you'll observe are a couple of things. One, the blue solution, which is the copper 2 sulfate, will start clearing out, right? So it will start becoming more colorless. Another thing you'll notice is that you're going to see a substance being formed on what is left of the magnesium that is reacting, all right? Now, the equation for the reaction is, okay, let me just get out of this here and go back forward. This. Okay, so this is the reaction that is taking place. It will be magnesium solid. Okay, why did that happen? Magnesium solid plus copper 2 sulfate aqueous to form magnesium sulfate plus Cu, right? So to explain what we observed, remember I said that the solution, which was blue before, will become colorless. That's because you're starting off with the copper 2 sulfate, which is blue, and you're producing the magnesium sulfate, which will be colorless, right? And remember I said that in addition to the solution becoming colorless, you're going to see a solid deposited. That solid deposited will be copper. So this should be solid, right? So that's basically the reaction here, the equation for the reaction. Now, this is, I'm going to show you now how this is a redox reaction. Firstly, what we're going to do, again, this is designating a molecular equation, right? So what we're going to do now is write down in the next step the ionic equation, right? So how do we get from the molecular to the ionic? We have to ask ourselves, okay, which substances will dissociate in an aqueous solution, right? Now, the magnesium itself will not dissociate because it's a solid by itself, right? So I'm just going to rewrite this here. But the copper 2 sulfate will undergo dissociation to form Cu2 plus aqueous and SO42 minus aqueous, right? And then on this side, you're going to have magnesium sulfate. Oh, by the way, this should be aqueous. Let me just say, the state symbols are very important when it comes to doing these things, right? So please don't forget that. Anyway, so the magnesium sulfate, an ionic compound in an aqueous solution, so that will undergo dissociation as well. And the sulfate will undergo dissociation as well. And the copper solid will remain, it will not break up to form anything else, right? So that's the ionic equation. So how do we get to the net ionic equation? We look for the common items on both sides, right? The spectator ions. So what would be the spectator ions in this particular equation? What remains unchanged as you go from reactants to product?
SO4.
Exactly. The sulfate ions will remain unchanged. So therefore, the real reaction would be Mg solid plus Cu2 plus aqueous to give Mg aqueous, Mg2 plus aqueous plus Cu solid, right? So this would be the net ionic equation, right? Now here, we can tell what is being oxidized and what is being reduced. So remember, the substance being oxidized is the one that is losing electrons, right? The substance being reduced is the one that is gaining electrons, right? We can also look at reduction and oxidation in terms of increase or decrease in the oxidation number, right? If the oxidation number increases, then that particular species is undergoing oxidation. If the oxidation number decreases, then that particular species is undergoing reduction, right? So you need to remember these things as we're looking at this here. So let's look at what's happening to the magnesium. Here, magnesium have no charge, right? But as you go from here to here, magnesium has a +2 charge, right? So therefore, the oxidation number is increasing, right? As a result of the magnesium losing 2 electrons, right? So therefore, we say that magnesium is undergoing oxidation, right? Because the oxidation number of magnesium is increasing from 0 to 2, indicating that magnesium is losing 2 electrons, right? And then now, when you look at the copper 2 plus, what's happening to the copper 2 plus as it forms copper, right? The oxidation number is what? Decreasing, right? Because the copper is gaining 2 electrons. In other words, the copper 2 plus is undergoing reduction. All right. So basically, that's what happening to the copper 2 plus. It's gaining 2 electrons. Its oxidation number is decreasing from +2 to 0, and therefore copper 2 plus is undergoing reduction in this process. And this is exactly what happens in every redox reaction, right? Something is undergoing oxidation, the other species or the other reactant has an atom that is undergoing reduction, right? And also one thing I want to point out here is that we can write down what are called half reactions or half equations for each for the reduction and oxidation. So in the case of magnesium, right, we can write down this to represent the oxidation half reaction. And then in the case of the copper 2 plus, I'm sorry, in the case of the copper 2 plus, it's gaining 2 electrons to form Cu solid. This is aqueous. This is aqueous, right? So basically, this is the reduction half reaction, right? And what is true for every redox reaction, without exception, is that whatever the number of electrons that is lost, same number of electrons will be gained, right? That is true for every single redox reaction, right? And this is something that you need to keep in mind whenever it comes to balancing redox equations. All right, I'm going to stop here for today, and we'll continue our discussion on Thursday. Oh no, your test is on Thursday. I'm sorry, my bad. Yes, so remember your test on Thursday based on chapters 1 and 2. And again, please forgive me for not grading chapter 2 in time. It's a large assignment, so grading it is taken up from grading up time. But I've posted the answer keys on that, right? So you can use that to review in preparation for your test number 2. And you can also see me during my office hours if you have a question, all right? Okay, so that's it. And for those of you out there in Zoom, I'm going to